Hi, my name is Eric Bassier. I'm Senior Director of Product and Technical Marketing at Quantum, and in this presentation I'm going to cover storage architecture considerations for machine learning at scale. In terms of the abstract for this presentation, the fields of AI and machine learning are at the forefront of driving innovation and discoveries across the globe. These fields generate massive datasets that require extremely fast processing, continuous analytics, as well as long-term protection and preservation. These requirements put pressure on traditional storage infrastructures, which are driving many research institutions to leverage new technologies including GPUs, NVMe, erasure-encoded object storage, and more. So during this presentation, which is about 20 minutes, I will outline some of the key considerations for machine learning at scale. I'll provide a reference architecture based on what we've seen our customers deploy, and through that I will also compare and contrast some different options, especially for the long-term preservation of this machine learning data. There's broad industry and analyst consensus that by 2025, 80% of all the world's data is going to be unstructured. The biggest subset of that data is video and high-resolution images used in industries across the globe, and there's a strong correlation between these types of data sets and the fields of AI and machine learning. Certainly much of what we're seeing is AI and machine learning being applied to gain insight out of large unstructured data sets. Here are some of the examples where we've actually seen artificial intelligence and machine learning being used across a number of different industries. As you look at this, I'd like to provide a few examples from some quantum customers. In the fields of healthcare and research, we're seeing GPU-based AI and machine learning being applied to study, for example, huge bodies of MRI images or CAT scans to start to identify patterns and find new ways to combat diseases and other healthcare issues. In the field of genomics, we're seeing this with genomic sequencing and microscopy data. In the field of media and entertainment, we have some customers that have very large content archives that are now using AI and machine learning to first index the content, but then get a better understanding of the type of content that they have so that they can find new ways to use their archived content and generate new revenue streams. And then with surveillance, we're seeing things like image recognition, object recognition within frames of videos being applied, and of course, many different applications within government. And we also see general, I would call it big data analytics, that's different types of data sets, but we're seeing this in industries as diverse as finance, manufacturing, where our customers are looking at yield data and telemetry data from the manufacturing floor to improve yields and study things like that. So these are examples that we're seeing where AI and ML are being used, and primarily it's on big unstructured data sets. That's kind of our primary focus as a company. Now, here are some different examples from some different studies of just how quickly these unstructured data sets and the bodies of data that are associated with machine learning can quickly get up into exabyte scale. Smart factories generating 1 terabyte of data per day, commercial jet 20 terabytes per hour, a bioimaging microscope 5 to 10 terabytes per day, an autonomous car, or even cars that are not fully autonomous but are part of an ADAS or automated driver assistance system, can generate many terabytes in a single day of driving, so that many of our customers in that space quickly get above an exabyte of data. So the first consideration or characteristic is just how quickly this data is growing and how quickly these data sets can get into the exabyte scale. That alone is one of the considerations of why companies are looking at different storage architectures. The data itself, when we kind of think about the characteristics of the data, Obviously, it's orders of magnitude larger than traditional corporate data, a database or a virtual environment. It's much, much larger. And because of that, it is impractical to store all of that data in the cloud. It's impractical both technically and economically. Now, that doesn't mean the cloud can't be used as part of an AI and machine learning kind of scheme with this type of data, but I think it's impractical that all the data gets stored in the cloud. We'll talk about that a little bit more as well. There's also a strong consideration amongst many of our customers of not having the cloud become a data silo. One of the things we see when we look at many of the traditional enterprise IT storage products is they've built fantastic products with a rich set of data services based on corporate data sets, databases, virtual environments, and many of those traditional data services simply don't apply or are not as effective when dealing with this type of unstructured data at scale and based on the workloads that developing machine learning algorithms really require. And I think the last thing is really where AI and machine learning are really being applied today, which is these big unstructured data sets are very complex to search and analyze. Now, that's a huge opportunity. Querying a database is pretty simple. I would say it's a problem that has largely been solved. But trying to find a particular image within, millions or billions of frames of video, for example, is a very, very difficult problem. And it's really where we're seeing some of these fields of AI and machine learning starting to be applied, again, to gain insight out of this unstructured data. So the data is growing at exabyte scale very quickly, high volume, high velocity. And the second important point is most of this data is going to be preserved and protected forever. We see this as a general use case or workflow when it comes to these large unstructured data sets. The first thing is when the content's created, it's being created by a machine. Or a device. It's not being created by a human being. It's one of the things that contributes to the scale and the volume of the data being created. There's always a stage in the life cycle of these data sets where very high speed ingest is required to upload that data to a central repository. And then that data is cataloged, it's processed, it is worked on, and it is often worked on and used by very highly skilled, highly paid individuals that are usually at the center of driving the organization's mission, right? Whether that's their business or a government agency's, mission or a research institution's research goals, right? It's usually at the center of what that organization is doing. And as these algorithms are being developed, some finished product is produced. In the example of developing automated driver assistance systems, which is one of the fields where we see machine learning being applied, it may be that a new algorithm is created based on how the car has been taught or what the car has learned. That algorithm gets deployed back out to the test fleet, at which point it's distributed in a sense. And the last stage is really where the content needs to be preserved and protected, often forever, at a minimum for many, many years and decades even, and in some cases forever. In the example of developing self-driving cars or automated driver assistance systems, those algorithms want to be kept forever and need to be kept forever because it builds up the corpus of data that can be used for building smarter machine learning algorithms, et cetera, right? So there's a strong desire to keep and build that corpus of data. The larger the data set is, the more effective the algorithms can be. And we see this in basically every field of machine learning. So this is kind of the general stages that we see. And when we think about data sets that are this large being having to be preserved and protected forever, this also really influences the storage infrastructure. Now, the most common alternatives that we see many scientists and researchers start with are two pretty common alternatives, and people tend to think of alternatives of either scale-out NAS, which has been used and deployed widely for many years in the enterprise, and public cloud storage. I think these are the two most common alternatives that people kind of start with. Now, there's some issues with both of these alternatives. I'd like to talk through those. The first thing with scale-out NAS is really has to do more with GPUs than anything else. Because GPUs have so much faster parallel processing power than traditional CPU clusters, it's often the case that the traditional scale-out NAS or enterprise scale-out NAS products simply can't feed the GPUs with enough bandwidth for what they need. That storage becomes the bottleneck. The second thing about using scale-out NAS is when it comes to that long-term protection and preservation, it becomes either prohibitively expensive to do this because many companies will either do this by replicating to, two different scale-out NAS arrays or systems, or trying to back it up with a traditional batch backup approach, which just frankly doesn't work as well. Doing things like snapping and all that become very unmanageable. And so there are some issues with scale-out NAS. Now, many people also look to public cloud storage, most specifically the public cloud object stores, and they have a lot of benefits. Obviously, cloud, very easy to use, and great kind of user experience around that. But one of the strongest considerations that we hear from customers is that these data sets are kind of their key asset as an organization, right? It's central to their mission. And I'm hearing more and more customers express this notion that the public cloud providers are kind of just a new data silo, and there's risk of that you've got all your most valuable data in a public cloud, but it's very expensive to get it out, very expensive to access it. Any type of access or especially egress can add up very quickly. And that can also be unpredictable, right? Not only is it just the absolute cost of it, but budgeting for it can be very difficult because it's very hard to predict what the costs are going to be based on what the retrieval patterns or access patterns to that data set will look like. We definitely see many companies employing a hybrid cloud strategy, and that means a lot of different things, but some examples that I've observed would be they keep their data on premise, often in an object store, and we'll talk about that in the next few slides, but they may then use different public cloud services to either help with their AI development, their machine learning. For example, an indexing service in one of the public clouds that can index the content that's in that object store, making it then easier to develop the AI and machine learning algorithms, right? So I think we view the future as very much being hybrid cloud and multi-cloud, meaning we believe many scientists will want to leverage different services and capabilities from the different cloud providers. And that's one additional reason why we believe it's good to keep the primary or golden copy of the data on premise in a place that's controlled and that is owned by the institution or the organization. So let's recap where we are now, and then we'll spend the last 5 minutes talking about some of Quantum's solutions for this issue. Most of the data sets are unstructured, and they're created by devices or machines. Because of the nature of the data and how machine learning algorithms work, these initiatives can very quickly generate exabyte scale data. GPUs are fundamental to this. They're being deployed and used. They enable massively faster parallel processing, and that can make traditional storage the bottleneck, especially scale-out NAS may not be fast enough. This data and these data sets are typically the most critical asset of the organization, so there's a risk of kind of putting that all in the cloud and not being, having that become a silo. The data has to be protected, but it simply is too big to just be backed up on the network every night. And the data needs to be kept forever. And so I kind of see this as almost the problem statement for data scientists and for users that are doing machine learning initiatives, trying to think about what is the right storage infrastructure, right? The best storage infrastructure needs to address these considerations. And that kind of gets to what we would advocate and what we're seeing our customers deploy. This is kind of a general storage architecture for machine learning at scale. Many of our customers use our file system called StoreNext. It is a high-speed scale-out file system. Typically, there is a high-speed distributed or parallel or scale-out file system of some type. It's not a traditional scale-out NAS system that's used for the ingest, the processing, and the analysis. Now, we're seeing more and more of our users deploy these file systems on top of NVMe flash, which, as many of you know, is a protocol designed for flash. It has much better characteristics in terms of just supporting the parallelism that's inherent in flash. So we're definitely seeing huge adoption of that. This would really be where data is ingested into that cluster from some type of a device. You have different data scientists and researchers that would work off of that cluster, that compute and file cluster. And this would also be where you would have your GPU analytics servers that are running analytics on top of that cluster. That's really the focus for the compute stage of this, that high performance stage in the life cycle of this data. And then we would see files and directories or objects moved to that long-term preservation tier, right? That online long-term preservation tier of storage. And that could be an object store, like quantum active scale object storage. It could be a combination of object storage and tape. It could also be the public cloud. And we do see that some customers are using all three. With our StoreNext file system, we have a very sophisticated data management policy engine and capability that allows administrators to move files and directories between all these tiers, almost treating all of these tiers of storage as an extension of the file system namespace, right? Now, we're definitely seeing that object storage is probably the preferred way to store this data forever for that kind of long-term preservation, because we can use erasure encoding to protect those objects. We can protect them across multiple systems and even multiple geographic locations to ensure that we've minimized the risk of any of that data being lost. Now, tape is very interesting because of some of its attributes, and I want to talk a little bit more about tape in the next few slides. Before I do, I wanted to share one additional reference architecture option that we've also been partnering with one of our partners, WEC.io. In this case, this diagram is kind of contrasting what a typical storage infrastructure may look like for more kind of corporate data, and then compared to a quantum and WEC.io cluster. In this case, the WECA file system is that distributed file system that's running on a compute cluster and then connects to the quantum active scale object storage over Ethernet. Similar to on the last slide, Quantum has worked with WECA. We have very tight integration with their file system, and their file system has the capability of treating the object store kind of as an extension of the file system namespace so that data can be preserved and protected there for many years at lower cost. Let's talk a little bit more about just technology options for that cold and archive storage tier. You've got flash, you've got hard drives, you've got tape, optical, cloud, and cloud is really, the cloud is just kind of, it uses all the same raw technologies that are here. There's nothing unique there. And then, of course, synthetic DNA. And synthetic DNA is something that we're looking at, and we're talking to some of the providers there. it's very low cost, it's very low power, it's very dense, and it's just not yet viable technically or commercially. I think that's something that we're going to be keeping our eye on, and it's certainly a very, very interesting field for the future of kind of archiving this type of content. And as we look at these types of storage technologies, you can see some of the pros and cons, but in many cases, we believe that tape does have some very unique attributes that make it very well suited for cold and archive storage. Now, the biggest issues with tape are it's difficult to manage and it's difficult to access and retrieve data from tape. There's not many applications or file systems even that deal with tape really well. But we think tape has a strong future here because tape has a very strong roadmap to continue to improve areal densities. And that's really what this chart is showing. This is from an excerpt from an INSIC report. And it's basically just showing that tape, or more specifically magnetic media, has a very strong roadmap to continue to improve areal density at a growth rate that's much higher than hard drives, right? This is why we kind of view that a lot of that high performance tier is going to be flash based, and even some of the new memory based technologies that are already being deployed. Much of the archival tier will be some combination of disk and tape, but a lot of the cold storage may end up on tape. And our goal is to be able to abstract that from the user to where storing data on tape looks just like you're storing it on an object store or on a public cloud object store service. This is really where Quantum's roadmap for our object store software is taking us. We've already got the active scale object storage technology with what we believe is the best erasure encoding technology on the market. We have done development work, and we have some patents already around erasure encoding on tape. And what we see as the future is that companies would deploy an object store on top of a combination of disk-based nodes or arrays, and then something that we call the quantum rail architecture, where rail stands for redundant array of independent libraries. So basically, scale out disk and scale out tape. If you are interested in this, please reach out to Quantum. We'd love to talk to you more about our developments in this area. So in summary, when you look at the portfolio that we have, it is really designed to meet any performance or cost target or requirement. And we've really built a portfolio that I think is ideally suited to meet some of those considerations of machine learning at scale. And I don't want to emphasize Quantum's portfolio too much. Wanted to spend this presentation talking more about some of the considerations, some of the different architectures, and hopefully leave you with some ideas of some different ways that you can build storage architectures for machine learning at scale. Thank you.